All right, so I'm going to try something different. We're going to do a recording through Teams this time, and I'm going to use Microsoft Word to do the work instead of PowerPoint. What I want to do is walk you guys through why the acceleration of gravity on Earth is 9.8 meters per second squared. So far, we've just accepted it. It's been 9.8. That's been all you needed to know. But now let's go ahead and demonstrate it using our equation that we've been using here. So I'm going to share the screen, and here's Microsoft Word. One cool thing about Microsoft Word, it has this thing called the equation editor. So let's go here and insert the equation. Yours won't be up here. I moved mine to be up here. But to insert an equation, you just go to Insert, Equation, and to make it look like mine, you can right-click and add it to the Quick Access toolbar, which puts it up here like mine. So anyway, here's Equation Editor. Wow, my computer's being very slow right now, and that's frustrating. I don't know why it won't let me edit that equation. So let's try a new equation here. There we go. Force of gravity equals G times m sub 1 times m sub 2, and you can see equation editor is turning it into an equation as we go. So it does caret for squared, and boom, it makes it a fraction. So I really like equation editor in Microsoft Word. That's how I make a lot of my Pogles. That's one of my little teacher secrets there, that how so many of my Pogles look so nice and neat. But anyway, there's our gravity equation. Let's make it big enough so we can actually see what's going on here. So for the Earth, right, we need to do a little bit of research. So let's open Google. I probably should have had my web page open there beforehand. So now we get to see my slow computer loading Google. Let's go ahead and close out of those things. We don't need to see what Mr. Billman posted 40 things of today on Facebook. So anyway, why am I going to Google? We're going to Google because we need to know some statistics about the Earth. So we need to know the mass of the Earth, mass of Earth in kilograms, and we're going to need to know the radius of the Earth, right? So let's, while Google takes forever, let's look at what's happening here in this scenario. So we want to know how quickly what's the acceleration of something due to gravity on the Earth. So here is the Earth. And where would something be that is on the surface of the Earth? Why won't it let me insert this dang thing? It would be, boom, right there at the radius, right? On the surface. On the surface of the Earth is one radius away from the center of the Earth. So we need to know the radius of the Earth, and that tells us our R here. We need to know the mass of the Earth, and that tells us M1. And what is M2? M2 can be anything. So let's say it's a person. I'm getting too fancy here. The person is going to be this tall red line. There's an object number 2, something on the Earth. And we want to know what's the acceleration on that object. So how are we going to go about solving that? I just copy and pasted our equation here. So we look at the free body diagram for that object. We always want to start with a free body diagram. So that object that's hanging out on the surface of the Earth there, I don't know why Microsoft thinks everything needs to be blue. It's kind of frustrating. Nobody likes blue. There's our object, and the only force on it really, let's say it's a floating object. Floating object makes it easier. The only force on this falling object, not floating object, would be gravity, pulling downwards. That's the force. That's the only force acting on this object. There's no other forces on it. We're going to ignore air resistance and all of that. So our Newton's second law equation on this becomes F net equals ma, right? That's always Newton's second law. And then F net equals Fg, because that's the only force. So net force is gravity. That's the only force, right? So when we add up all the forces in the y direction there, gravity is the only one we get. So gravity is the only force in the y direction. I'm sorry, this is kind of going a little slowly, but that's partially because my computer is very slow and partially because it's the first time I've tried anything like this. But let's recap where we're at so far. We've got this object that is falling down on the planet Earth here. It's like a skydiver or something like that. We've got the planet Earth here with a radius, and we've got our free body diagram here on that falling object that shows that gravity is the only force acting on that object. So then we use Newton's second law to look at the net force on this object, and we get that the net force is just gravity. Gravity is the only force, so it's the net force. Gravity equals ma. Let's add that, actually. Gravity equals m times acceleration. We know that because gravity's the only force. So any acceleration on this object here, any acceleration that's on this object right there, is from gravity. So gravity equals mass times acceleration. So what is the mass of object 2? It's this right here, m2. So let's go back. This equation here, our main equation for gravity, but we know one more thing about Fg. Fg equals ma. So we know all of this, not only ma, but m2 times a, because m2 was the object, right? m1 was the Earth, m2 was the object. So we know that m2 times acceleration equals g m1 m2 over r squared, our equation for gravity. Well, hey, check this out. We've got m2 on this side of the equation, so let's go ahead and we don't need this. We don't need this anymore. So now let's just look at this. Mass times acceleration equals gravity. That's all this says. We just are using different ways of showing it. So over here we have mass times acceleration for this falling object, object number 2. And over here we have gravity, Fg. We're just using our equation for gravity now, g m over r squared. That's the equation we'll use for gravity for planets or whatever. So what? That was frustrating. Come on. Microsoft is frustrating sometimes. There we go. So what happens if we were to divide both sides by m2? Well, m2 would cancel out over here, and m2 would cancel out over there, and boom, we get that acceleration from gravity on planet Earth is equal to g times mass of planet Earth over radius of planet Earth squared. So it actually, the mass of this object didn't matter at all because it canceled out, right? It's over here on the net force side, F net equals ma, so we have m in that. And also force gravity up here also depends on mass. So since the total overall force and the force from gravity both depend on the mass of this object, they end up canceling out, right? It divides out of both sides, and so mathematically, the mass doesn't matter, which is something Galileo demonstrated way back in the day with the bowling ball and the smaller, I don't know, golf ball sized object or something like that. He took a very heavy large ball and a very light small ball, dropped them off the Leaning Tower of Pisa, and they fell at the same rate because mass doesn't matter for acceleration of gravity. The balls there, the large ball and the small ball, were both m2. and they both canceled out. The only mass that matters when it comes to acceleration in a gravitational field is the mass of the, the object creating the accelerating field. So in this case, the mass of the planet Earth, is what's causing this acceleration gravity field around the planet. And so that's why it's 9.8, because when we plug that in, let's go ahead and plug that in now. So G, which is 6.67 times 10 to the negative 11. Let's do this in equation editor, actually. 6.67 10 to the negative 11 newtons times meters squared divided by kilograms squared times, and let's go back here and get mass of the Earth, 5.972 times 10 to the 24. 5.972 times 10 to the 24 kilograms, and we want to divide all of that by our r squared, so we need radius of the Earth in meters. 6.371 million meters. Well, that's helpful. So 6.371 million meters squared. And there we go. So we plug that into our calculator, and we'll get the answer. So this actually gives me a chance to show you one of my favorite little tools on a computer, which is Wolfram Alpha. And actually, one of the cool things about Wolfram Alpha is it knows all sorts of science as well. So you could literally type in like 5 times mass of the Earth, and I think it would even like spit it out and be like, yeah, mass of the Earth. We know that. Yep, exactly. Boom. That's what it says. It even has the little symbol for mass of the Earth. So Wolfram Alpha is a calculator, but you don't even need numbers. You can punch in whatever you want, and it can find the numbers for you most of the time. It's the smartest calculator out there. But anyway, 6.67 times 10 to the negative 11 times 5.972 times 10 to the 24 divided by 6.371,000 squared. Wolfram Alpha, I also love it. It shows you the math in case you made a typo with your parentheses. It would show up here because one of your fractions or something would be wrong. It's great. And lo and behold, 9.8, 9.8, right? We already knew that would be the answer. We were just making sure. 9.8 meters per second squared. So we were kind of all over the place there, but let's recap. Let's recap what we just did here. So we started out here. Here's the Earth, and here is a skydiver that hasn't opened his parachute yet or anything like that, just falling. So we look over here to the right, we've got the free body diagram of skydiver falling, and the only force acting on skydiver falling, because we're ignoring air resistance and all that, is gravity. Gravity is pulling skydiver down. That's it. So then we go to Newton's second law, F equals ma, for the skydiver. And we go, well, okay, the only force, F net, the only force is gravity. So we get Fg equals ma. So Newton's second law became this here. The mass of skydiver, we're calling m2. We're calling Earth m1 here. So mass of skydiver is m2. So we plug that in here for ma, right? ma is now m2 times a, because this is the forces acting on this skydiver here. So maybe I should write that in. Will it really not let me type in here? That is frustrating as heck. Okay, whatever. This is m2. Skydiver is m2. Earth is m1. And we know that that's equal to the force of gravity. So we know we know force net, which is ma here, is equal to Fg. Well, what is Fg? This is Fg. This is the equation for gravity. So we set net force equal to Fg. When we do that, we see that the masses cancel out. That m2 here, mass of the object, mass of the skydiver in this case, cancels out. We're left with the acceleration due to gravity of any object on the planet, because you can see the mass of that object is no longer even in the equation. So it doesn't matter how big this object is, it's going to be accelerating here because that's what we're left with, a. There's no more m. We got rid of m. All we're left with is a. So the acceleration from gravity at this spot here, anywhere around the surface of the Earth, is going to be the same. It's going to be equal to this, which we punched in here. And then through Wolfram alpha, we got that it's 9.8. So hopefully that helped. Now you understand a couple things. You kind of understand one way we can use this equation. So say we discover a new planet. We do some calculations on its orbit, doing something called circular motion, which we'd learn in Physics 2 if we ever get a Physics 2, all about circles and things moving in circles. And through that, we'd actually be able to calculate its mass. And, you know, through basic telescope observations, we could calculate its size, assuming it's close enough. And so we can get its size and its mass. We could actually figure out the gravity of faraway planets this way. So any planet, the acceleration from gravity is going to be this equation. You take g, the 6.67 times 10 to the minus 11 here, multiply it by the mass of the planet, and divide it by the radius of that planet squared, and it will give you gravity. So bigger mass, bigger gravity, larger radius, though smaller gravity. So it's all about the mass and the radius. And that's it. Hopefully that helped. So yeah, I just wanted to come back here now and sign off. I might throw an extra credit question onto the quiz whenever our next quiz is. We're going to have a quiz coming up here pretty soon, but I'm kind of procrastinating that because I don't know how online school quiz is going to work. Probably just be a take-home quiz, to be honest. I trusted you with that earlier in the year. No reason I can't trust you with that now. So I'll toss an extra credit question on there where I give you the mass of some other planet, maybe a real planet, maybe one I make up, who knows. I'll probably find, Xandar from Guardians of the Galaxy. Let's do Xandar. I'll see if I can find the stats on that. And you will calculate the acceleration due to gravity on Xandar. So those who watch this video, you're going to get those extra credit points, hopefully. Don't tell anyone else, though. We want that to be for the people who really took the time to watch this video. So extra credit coming your way on the quiz, as long as you remember how to calculate that acceleration on a planet. It's just g, 6.67 times 10 to the minus 11, capital G, times mass of the planet divided by radius of the planet squared. And that will calculate acceleration of gravity. So I will see you guys virtually for notes tomorrow, I think. Wait, no, I don't know. Whenever there's next notes. So thanks.